So this is sixth lecture about machine learning, and today it's a great day because I think that finally you are all ready. If you have followed all 5 previous lectures, you are ready for neural networks. Which we are going to talk about today. So, as you can know, that basic strategy in machine learning is to find something that you need to optimize. For example, you need to classify apples and bananas, and you want to find some function which looks at the photo and tells you, is it a banana or is it an apple? And to do that, you need to minimize something. And during 5 previous lectures, we've talked about how to minimize, how to use derivatives, and all this math stuff about optimization, which is like the final. We are talking about machine learning. In the end, we have optimization of something, and above this we have some function we want to optimize, and there we have some data. So we have just some numbers, some pictures, then we have some function, and then we try to optimize this function in order to classify our data, or for example, if we are talking about games, we want to win a lot of games, and we want to increase our win rate or increase our reward. So we basically, in every machine learning task, we need to optimize something based on data. And data can be created manually, created by humans, created by some hardcore other programs, or it can be created from environment, from game environment. For example, we can talk about poker. And in poker, you have a hand of cards, and you, for example, want to know how winning this hand of cards is. And in that case, you can just play a bunch of games of poker and write down all your hands, and then write down if you win or lose. And then you can optimize this data and gain something about this function, and finally you can answer a question if this is a winning hand or if this is a losing hand. But and we talked about a lot about optimization, but we still don't know how to find this function and how to define it. And in previous lecture, we've talked about linear regression, and this is something similar to it. So as you can remember that if we have some data and we have some data points, so we have a list of these coordinates. So we have these coordinates, and we want to find the best line which fits these coordinates. And this line can be described by this linear relationship. And you remember that with using partial derivatives, we've optimized with, firstly, we deduced some loss function, which was equal to squares of distances between our between data and desired line. And then we optimized this loss function, which we will usually denote as such letter L. And we optimized it by parameters A and B. So basically, after we have some data, and we define loss function, which can be defined by different ways, but we will talk about mean square error, which is the most common, is the easiest one. And after we've defined our data and loss function, we have some parameters in function we want to optimize, and this is the function we want to optimize to get the best fit line. And in that case, we get that loss function is some function with variables a and b, and then we try to optimize loss function and find the best fit function. So this is basically machine learning, and it's mainly used in part of machine learning which is called supervised learning, because we talk not only about x values, we also give machine y values. You can see in this list we give x coordinates and y coordinates, and sometimes x coordinates can be like lists of lists, so it can be more complex than just one number, but nonetheless we have whole the structure which is called supervised learning. So we give machine some x data, some y data to learn on, and then machine tries to find some patterns in this x and y data and find the best function to to optimize loss function. So this is how supervised learning works. But here's a big question: how to define this function? In previous lectures we defined it as linear regression, but we don't need to, because in most cases this function will be and this dependence between x and y values will be much complex. For example, if we talk about again about winning hand, all these combinations in poker can be quite sophisticated, or if we are talking about like social income of a person, and it can be influenced by a lot of factors like his or her job, by country, by relatives, so a lot of different parameters, and these relationships are not linear usually. So this function works only if we want to, and that's when we introduce neural networks, because neural networks can optimize and they can behave like a lot of functions, and they are sometimes called universal approximators, which means that neural networks can mimic any function we want. And by any, I mean some differentiable and continuous functions. So if we want to get this machine learning working, this supervised learning, then we need to define somehow this function, and we will define this function using neural networks. And in different cases, we will have different neural networks with different structures. So that's why we basically use neural networks, because they are so wide and they can be any function you want, any function you desire, based on data you get. So what's neural network? In early 40s, scientists were conducting research on brain cells, and they wanted to know how brain cells have so complex behavior, so complex that we can think of such complex things as neural networks, and they introduced the most basic unit, a neuron, which is a cell in brain, and they tried to mathematically research it and write something approximations about this cell, because biologically this cell is quite complex and it's quite sophisticated to approach it from biological or physical study, so they tried to approximate and give some results. So that's what they've came up with. This is called Neuron, and we are not confusing it with a real neuron. So right now it's only a mathematical abstraction, and it has three crucial features. So first one, it's inputs. So here we have different inputs, and there can be as much as you want of these inputs. Then we have this is like a brain of a neuron, a main, the most crucial part, which makes all these calculations. And then we have output. And output only one, so output has only one value to be shown. But this output value can be distributed later on in different directions. And all these values will be similar. They will be equal, but they will be equal and will be equal to this y. And all these values can be then distributed to other neurons. So in the end, we have new neurons, and this output becomes an input to a new neuron. So we have this the most basic unit, and we will then construct a lot of different structures from this basic unit. So after we've defined inputs and outputs, we finally can define this part, which is called calculation part. And usually we can calculate y by this formula. So we have some function, which we will talk about later, taken from sum of inputs multiplied by some constants. And these constants are called weights. So these are weights. These are inputs. This one is output. And these weights, they are connected to each connection. They are bounded to only one connection, and they totally define it. So, for example, some neuron can have quite big weight, and in that case, this connection will be quite crucial for this neuron. And for example, if this input has weight around 0, then this connection will have a small impact on whole this sum. And that means that this output will be much smaller affected by this connection. And also these weights can be not only equal to 0, but they can be positive, they can be negative, and these weights basically define how neural network will behave, and we will try to, and these weights are basically will be our parameters that we will try to minimize them. So we can rewrite this as sum again function, and this function called activation function, and we're going to talk about it right after this. And it can be rewritten as a sum notation. That means that we are summing inputs multiplied by weights, and then take activation function from whole this sum. And why do we use activation function? Why don't we just use without sum, just use output is equal to sum of products? because usually these sums can be quite large or by module, and we want to bound output values in some boundaries, for example, from 0 to 1. Take a look at this example. We have some neurons, some inputs, and we give this neuron inputs from different neurons, and then we read output, and this output should be like indicate some probability. And probability is always bounded between 0 and 1. And if these inputs are quite large, then this boundary can be broken if we are not using activation function. And also if we are using activation function which will create non-linear behavior. And that means that all inputs are not just equal to a sum, but then the sum is squashed between some boundaries, and we can take a look at 3 different types of activation function. So first one is Sigmoid. Which was given for you as an example of taking derivatives, and its graph looks like this, and it's bounded between 0 and 1. And it's perfect in a lot of neural networks because we usually want to create some non-linearity, and you can see that it's not comparable to just a simple line. It has much complex behavior, and its boundaries won't go below 0 or above 1, which is also good. And another function is called hyperbolic tangent. It was also given probably as an example. And this function is bounded between 1 and -1. And we can sometimes have, for example, this is like maximum income, and this is maximum loss, and this is some trade marketing, and we want to get some good reward or predict stock prices, and in that case we can use hyperbolic tangent because it gives not only positive values like sigmoid function, which is good for probabilities and probabilities of something being something, but it also gives negative numbers. And final one is called ReLU. And it's quite simple. It's just equal to 0 and then goes up as a line. And it's called ReLU. And it can be described as 0 is x is less than 0, and x if x is bigger than 0. And it's not a line. It has this non-linearity. That would be a line, but that ReLU is not a line. And it's used mainly in image recognition because it's so simple and it requires much less computational power than sigmoid function and tangent. And ReLU is probably one of the most common activation functions. But we will stick to sigmoid function for a little bit because it shows this idea of squashing everything into boundaries between 0 and 1 to create sense of probabilities. For example, we can use this like we can ask then later neural network about, is this an apple or a banana? And it will tell with probability between 0 and 1. That is like with 99% it's a banana, and with 1% it can be an apple. So this is what defines totally neuron, the most basic part of neural network. This is three things: inputs, activation function, and summation, and output, which can be later distributed to other neurons. And usually in neural networks, these neurons are then grouped into layers. And these layers can be later connected. For example, this is neural network, and we give to first layer of neurons some values, 0, 1, 0. Then we connect each neuron, this neuron called input, and it has only value and it doesn't have outputs, squashing function, activation function, and summation. And then we distribute this 0 between other neurons of the next layer. And then we get some values. And then we distribute to the final layer, which is called output layer. So this one called input layer, and there you have only values. This is called hidden layer, because we don't get these values. They are automatically processed by computer, and then we get output. If we are treating this system as a black box, we are not interested in these values. We are interested directly in this. And these neurons have outputs and summation function, and these outputs we receive on a screen, for example, and that's why this layer is called output layer. And that's how we can group neurons into first input, then hidden, then output layers. And this architecture defines neural network in some sense, and there can be more than one hidden, or there can be only 0 hidden layers. There can be but usually such neural network has only one input and one output layers. And as you can see, this neuron, this input layer neuron, distributes all its values into all hidden neurons. And it happens with each neuron. So each neuron of the previous layer is connected to each neuron of the next layer. And such structure, such connection, is called feed-forward neural network. So, for example, if we have the 0, then the 0 is multiplied by this weight, for example. This weight is, for example, is equal to 1. 0 we multiply by 1, it's 0. 0 plus 1 multiplied by other weight, like 0.5, 0.5, and 0 multiplied by one weight, which is equal to -1. And we get plus 0 equal to 0.5, and then we can squash it using activation function. And we get some 0.7. And then we repeat this procedure with hidden neurons if they are treated as input neurons. And we do the same for output neurons and later on. And then final values which we get, we receive as an output. And this means that whole the structure can be treated as just a black box, which we've talked on previous lectures. And so we have 3 inputs and 2 outputs. And somewhere in between, we have hidden layers. So that's how we can treat neural networks. So let's code. Let's try to code and create this shell of neural networks. So first, we have our Jupyter notebook, and let's scroll down a bit. So here you can see neuron formula. There you can see some text about layers. You can see this picture, which is what I've just drawn, representation of feed-forward neural network. And you can see that arrow indicates that that data from inputs is distributed to hidden layer and then to output layer. And we can see as input, as data travels from input to hidden to output layer. And it's like traveling forward, and that's why it's called feed-forward neural network. And now we are trying to implement this in Python. And first we need to define some final structure in Python, which we are going to use, and it's called class. So we will use this for neural networks because sometimes you can't just use only numbers or lists, and because they have only defined functions, and sometimes we need something more, and we need to create new objects with new properties. And then that's when we introduce classes. So each class can be defined using function def init, and then we can add some new functions which will do something new. For example, if we want to create a class called triangle, this is how it looks. And first we will need to define triangle. This is new object. So we define it by setting its coordinates here. And then we want, for example, this triangle to write down all sides it has and to write down its area. And then plot itself, for example. And we don't want to do this over and over, and that's why we introduce class. So here you have an example of such function where you just return all sides. There you have a function which is called area, which calculates area by Heron's formula. And finally we can use it, and it will look like that. So we've defined 0, 0, 1, 2, 3, 0 is called coordinates of points of triangles, and then we've calculated length of each side and calculated its area and plotted. And you can see that it works. And neural network has the same problem. We don't want to do the same tasks over and over. Let's just create new object which will be called neural network. So you can also access a lot of all variables that each class has. So it's a very handy and very easy way, natural way of defining objects. So now we are creating class which is called neural net, and First of all, in this part of lecture, we will just define a skeleton of neural network, a shell, which we only will assign values of weights, and that's it. So that's how we will represent weights as a table. And first, so let's look again at this network. We have 1, 2, 3, 1, 2, 3, 4. We have 3 input neurons and 4 hidden neurons. And we want to somehow store weights. And we can do this like following. We can assign index to each weight. And it will be done like that. 1, 2, 1, 3, weight 1, 4. So this is how it will be stored. You can see that the first index is the same as input neuron, and the second index is the same as number of index of hidden neuron. And in Python we can easily do this using lists of lists. So first we define a simple list, and then we fill this list with lists too. So we have list of lists. So it will look like that. We have a first list, which will be all weights of connections which are going from first neuron. Weight 1, 1, weight 1, 2, weight 1, 3, and weight 1, 4. And then we have second list, which are all connections which are going from the second input layer. 2, 1, and 2, 4. So it will be 2, 1, 2, 2, 2, 3, and 2, 4. And finally we have we have 3, 1, 3, 2, 3, 3, and 3, 4. And then we can access all these weights if we want to by following structure. For example, we want weight which is coming from first input neuron and then goes to third hidden neuron. In that case, we first use square brackets and write 1, and then we access this list, or list of neurons which are going from the first one input neuron. And then we write in square brackets 3, and then we access third and last, third hidden neuron. And that's how we get weight of connection between first input neuron and third hidden neuron. And you can see that here we have a table representation. So here we have a list, then a list, and a list. So that's how we are going to define weights. And usually, if we are defining neural network from scratch, then we are assigning random values to a weights, because we want neural network not to be biased to any new function. So we just assign random values and then watch what will happen. So that's how we create this list of lists. You can see that's what I've talked about. This is weight like 1, 1. This is weight 1, 2. This is weight 2, 1, which is coming from second input neuron into first hidden neuron, and so on. And we can see here we can see more of like table representation. Here we have neurons which are coming from first input neuron from second neuron, and from third. And the same can be done for, so here we defined the first table of connections from input to hidden layers, and now we can do the same and treat hidden neurons as input one and output as hidden one. And we can define the same table, but it will look like from first it will look like that. So each hidden neuron has two connections to each output neuron. And here we have all neurons which are coming from the first one, hidden neuron, and here we have from the first one. And this is neuron which comes from the first hidden neuron into second output neuron. And here we have activation functions. We can see their graphs. Sigmoid function, which is squashed between 0 and 1. Hyperbolic tangent, which is squashed between 0 and minus 1 and minus 1. And ReLU, which goes like that. And here how we can define sigmoid function. It's very easy using the most basic library, math, which we've talked about on the first lesson probably. And here we finally define this class, which is called neural net. So first one, we define it like using so this class will, the main task of this class right now is to define weights of neural network which has such structure. It has one input layer, it has one hidden layer, and one output layer. And we define number of neurons in input layer, in hidden and output layer. These are main parameters, and then we create table of weights and define also activation function for this class. And here you can see that we define this list of lists, then we fill this list of lists of weights, and here we have sigmoid function. And here how you can use it. So firstly you define object by class neural net, then you define this, that this object has 3 inputs, 4 hidden neurons and 2 outputs. And also you define boundaries in which random weights are assigned. And here you have printed out first weights of connections between input and hidden layers. And that's it for this part of this lesson. And in the next part, we will define meat of neural network and hold this calculation process.